I would like to thank the organizer for invitations. And this is the title of my talks. I will talk about the correlations between for the Higgs decay to diphoton and Z gamma channels from the new scalar contributions. And this talk is based on these three papers, and mainly from the first one, and in cooperation with Professor Cao Xianggen, Dr. Cai Yuxing from National Tsinghua University. Okay, this is the outline of my talk. First, I'll give a brief introductions, then I'll perform our calculations to Z gamma with a new scalar contribution, then our result in implication, then I will conclude I will give a conclusion. So I think it is fair to say the case for a TeV scale machines is based on these two arguments. That is what is being told in this talk by various speakers, that unitarity actually required that the mechanism for the electroweak symmetry breaking was manifest at or below the TeV scale. So this should be something around this scale. So we have to prove it by machines. Then the other one is more like a theoretical argument that the standard model is unnatural and incomplete, some sense like hierarchy problems. And indeed, this was being told many times. Last year, July 4th, there's a particles Higgs, standard model Higgs-like was being discovered. Then it looks like this. Both discovered by Atlas and the CMS corporations at CERN. So if this is the pictures of Higgs, so what this really means? It really means like this. This is the pictures. You are not really very clear whether this is a Mr. Higgs or not. Then, after accumulate of more data early this year, March, in Montreal conference, we have accumulated up to about 20 inverse femtobonds. Yeah, indeed, it's more and more like the Mr. Higgs now. Yeah. Then theoretically, scalar sectors is the most theoretical uncertain factor, and also the least tested experimentally. Then I write down all these terms are relevant to scalars. For the first term, this is the vacuum energy of field. Then it's reversed to it will reduce the aspiration expansion of our universe. It's obvious, well-known fine-tuning problems. And for the last terms, this is the Yukawa couplings and the schedule invariance, and give the masses, but we still don't know the flavors problem. Why there's the mass hierarchy among the fermions? It's obvious that CK mechanisms can fit CP and data quite well, but the strength of CP phase is still too weak, too small to explain the fermion symmetries of the universe. The second term is the quadratic term of scalar mass terms, which is actually the origin of the so-called hierarchy problems. We don't know. And the third term, lambda. If this 122, 125, 26 is indeed the standard model Higgs, and according to these many efforts, according to just calculate the next leading two loops, for example, two loops affected potential corrections, and three loops are Girondins. All of this just based on the next leading order within the framework of standard model. And they also calculate the lifetime of so-called meta-stable of the vacuum state. It's once we really live at the age of the universe. The 123 vacuum energy actually is quite stable. So this gives us another fine-tuning of our different insights. Probably this really means something. We don't know. So what is standard model Higgs? The standard model Higgs is quite simple. So all the properties are just telling me for a given mass. So 123 actually give you 26, actually give you everything. So theoretically, we have to know better for this theory. So if it is 126 GB, then the decay weeks, and all these uncertainty are coming from the uncertainty of the masses of fermions, and the strong coupling, etc. So theoretical question to address the new physics. And so any deviation from this indicate new physics. So we have to know the standard model couplings, all the standard model coupling to not in both gauge fields but to fermions. And are there additional field scalars? Are there composites? Just like previous talks. And any invisible decay modes? That's theoretical question to address. And experimentally, we noticed there's about four kinds of production channels for Higgs. And so far, they only Higgs decay to gauge bosons, especially to dipole gamma gamma ZZ and WR was found. And the non-fermionic decay channels were discovered yet. And this challenge by solving the small branch ratio and the backgrounds. So just a brief data. This is the 126 peaks for DD channels and gamma gammas. And especially interesting is the diphoton channels. According to data, it seems a little bit larger than the predictions of standard model. For this is from LATAS. It's about 1.65 times larger than the standard model predictions. For the CMS results, previously for the 70 eV data, it's about 1.7 larger than the standard model prediction. But after accumulating more data, like for example 80 EV, it dropped down to 0.5. So average is about 0.7. Different analysis, different cut. But at the moment, since I'm going to talk about the correlation between D gamma and gamma gamma, so whether this is enhanced or suppressed doesn't matter. So, but at least, but now we just take this gamma gamma as enhancement for the moment. At the moment, then the parity of the Higgs seems to be scalar. But we have to bear in mind the mixture states between for the pseudo-scalar is reliable. So for this, to study the Higgs, to address the beyond standard model physics, we have to study the branching ratio, especially for Z gamma, Z gamma, gamma gamma, because these three channels are loops. Higgs decays to loops, so we are sensitive to physics beyond standard model. And we also have to know to measure the branching ratio to fermions, so whether this is Higgs really give fermion mass, and the partial decay width to WW and ZZ. This will tell us the electroweak symmetry breaking structures, really standard model or subdeviations. And this talk I'm concentrating on Z gamma and gamma. So the standard model contribution for gamma gamma is from the diagrams. This is configurations, and this definition for this complicates functions. But simply says is the W loop channels are dominant channels. To give the strength of this guy is about minus 0.8, and the fermions give the opposite sign is the plus, about plus order 1. So W channel is dominant. And the Z gamma standard model is, again, the fermion is almost suppressed. So the main contribution is from W loops. This used like that. So what's the advantage to study both Z gamma and gamma gamma? And if there's a new particle running in the loops from the Higgs decay, and for the gamma gamma, the two legs that only can sense the charge, the quantum number of electric charge of the running particles. So if we replace one leg of a photon by Z, then this leg of Z, it can sense both hydrocharge and isospin quantum numbers. So if we have two channels being discovered, then we will be able to pin down the quantum structures of probably new particle running in the loops. That would help us. So then in this talks, we just consider the new scalar's multiples contribution in the loops. There's a twofold. The first one is that most of models beyond standard model contains extra scalars, singles, doubles, triples, and more, etc. And the second one is we found most of the formulas that used in the literature for the Z gamma of new scalar contributions are not consistent with each other, so it deserves to be divided. So we started from a general scale with isospin T3 and the electric charge Qs, and this is the relevance couplings to the calculations. We have two party terms during the new scalars to the standard model Higgs, and the important is this term, this last term, they will give the mass readings at tree level for the new scalars multiples. And we are going to argue that degenerate spectrums for the S multiples is a very good approximation, and I will convince you later. Now we just take this simplest for our calculation. Just take space multiples is degenerate. And this is the gauge interactions and these quantum numbers for this extra scale. So this is just calculations. So we found that this is our result. The important is after we derived this, we found that in the literatures their result different from ours by the actual minus or minus 1/2 or minus 1 cosine theta w or different combination of this one. So if you take the ratios for the Z gamma to the standard model, and also the gamma gamma to the standard model contributions, you can make this quantity R Z gamma and R gamma gamma. And due to the different amplitude sign, as I just pointed out from others, we will lead to different results compared to others. And the point is our formula for the Z gamma decays will retains the gamma gamma modes when we take MZ mass goes to 0 and gauge coupling go back to the charge quantity. And this is also worth to mention that there's another groups in Taiwan National Central University led by Professor Zheng Weijiang. They also study a similar study, but they concentrate some models which are relevant to neutrino scalar extensions, and they are using the so-called Passarino-Veltman functions, and our result is consistent with theirs. So you can see if the mass splittings here, if you can take a Taylor expansion, this mass splitting was constrained by the STU parameters, which can be as large as only about 30 GeVs. So, and this MS is presumed to be a few hundred GeV. So the modification for the non-degenerate to this calculation would be just a few percentage. So the degenerate case is a very good approximation. So this is the result. So we just starting from, okay, so if this S is a singlet or doublet, then the quantum number can be written like this way. And we found when again this blue is the photon, and red dash 9 is the Z gamma. If gamma gamma is enhanced, just like what experimentalists tell us, for the singlet case, the Z gamma will be suppressed, and for the W will be less enhanced, but it's enhanced. So in other words, this is anti-correlated. This is positive correlated between Z gamma and gamma gamma. And the reason is the following. So we just relook at the gamma gamma ratio. We found the new functions. As I told you, the 1 and A1 half is the standard model contribution, and the W is given negative quantities, and the positive from the top part, and W is the dominant one. And we can find that the new scalar contribution is the opposite to the standard model contribution. So in other words, this red circle part is negative sign. So, and the Q square, of course, is positive. So in order to have constructed interference, or in order to explain the enhancement of the photon-photon channels, the trilinear commute should be negative. But anyway, so once this one is fixed, for the Z gamma is also fixed, because the only difference is just the leg attached to the Z photon. So the only difference is this one, this part, this part. This part is one is from charge, the other is from the Z coupling. And this one for the Z gamma, the function is both positive compared to in both standard model and they are same sign. And so if this is negative, so whether this Z gamma is enhanced or suppressed, this can be only determined by the structure, the quantum number here. In other words, just the quantum structures or electroweak quantum numbers of the new particle running in loops. It's irrelevant to other parameters. So if this one is greater than 0, then D gamma will be enhanced. Otherwise, or the other way around. So by this one, we can just easily understand why the singlets and doublets both have a different behavior. And we can notice that our result will be different from the others in the literature. So it would be easy to tell by rewriting this charge as shown here in terms of isospin and hypercharge. I'm sorry, here that y should be absolute value. So this one is always positive. So whether the quantity of this guy is depending competition of hypercharge and isospin. So what if this actual scalars are higher multiples under SU2, then the contribution will dominate, and this quantity will be positive. So we just play another example. For example, take a triplets, which are well motivated from, for example, the complex triplets are nothing but just type 2 seesaw mechanism. And we found both cases are enhanced when it are positive correlated to photons. But for y equals 0 case, the enhance is larger. The reason is because the hypercharge is 0, so these quantities get enhanced. So it's interesting to see that recent paper by Okada, they also studied the type 2 seesaw mechanism, and there's a statement in their abstract. They found that diphotons and the Z photon channels with respect to their standard model expectation, and they found that the decay rate of these two processes are anti-correlated. This is their result. One is Z gamma, and the other is gamma gamma. And independently, because we have a result, we have a formula, so we can easily understand that. And we found that there's mainly positive correlated between these two, and only a very narrow regions are anti-correlated. The difference from the results is because the formula actually show you there's a negative sign. The second one is they're only taking into account the W charge contributions, but the triplet we know that's additional single charge. So you have to take into account for these two. And that would be interesting because if you fix the benchmark for the W charge and to see the effect for the single charge, because single charge is in the middle, the hypercharge, the isospin, the third component isospin is 0, according to our formula. According to our formula, this term is strange, so this quantity is negative. So the result will be anti-correlated. And for the W charge contribution, it will be positive correlated because isosmooth. Then if you combine both, there's only a very narrow regions which are positive anti-correlated. It's different from that. There's so then this is just a small advertisement, and we have a very predictive neutrino mass models using a higher multiplets such as phi. And this is the normal hierarchy, and the derived CP phase and the absolute value, absolute scale of neutrino mass can be determined by the rate A. For example, mu to E gamma, etc., etc. And we study this because this is a phi. So anyway, we know the result. We know the general functions. So so we can just then we generalize our discussions to arbitrary case, and we found there's a asymptotic saturations behaviors for these ratios of the Z gamma. For example, for the higher isospins, that will saturate about 1.5. So it cannot larger than 1.5. This is very good indications for experimental probe. On the other hand, if the fields have a larger hypercharge, then it cannot be go down lower than 0.86. Here we're using some asymptotic behavior of functions. That you can show the correction is quite small for parameter, interesting parameter space. So we can then furthermore we can generate. So far we have only one extra scalar. Actually, we can generalize to the arbitrary numbers of the scalar multiply with mass, lambdas, and degeneracy of this particle, as long as they are constructed interference for the diphoton channels to the standard model attribution. Then we have a general bounded for our relations between Z gamma and gamma gamma. So if the photon-photons ratios to the standard model is about 0.5, then between 0.5 to 2, then the Z gamma contributions from the new scalars independent of their numbers and common number, their company of their and their common numbers, it will be just directly within of this in this range. If any probe is different from that, then you can it will be a very good tool to test the physics behind standard model. And the conclusions, precision measurement are needed to answer the questions whether this is the Higgs or predicted in standard model. And photon, Z photon are sensitive to physics of standard model, and therefore related and study is simultaneous measurement will able to tell us proper quantum structures for the new particle running in the loops. And thank you for your attention.
Any questions for Dr. Chen?
If X to gamma gamma goes to 1, close to 1,
Yeah.
then what's the...
Then Z gamma goes to 1.
Goes to 1, sure. Standard model.
Yes, thanks.
Any more questions?
Just one comment. I think the last statement might not be correct. So you can, in your you just keep the standard model, actually gamma very close to 1, but you still has room to make gamma Z different from whatever standard model prediction is. It still have a lot of room to do that.
Yeah, it's still a lot of room. Here we have a very straightforward and simplified case. Yeah, that's true.
Dr. Chen.